Hello, good day again everyone. Welcome again to Integral Calculus. And in today's video, we would be discussing about integration by substitution. So when you are to deal with an indefinite integral, the first thing that you would be doing is to check if the equation that you are trying to integrate can be solved using these basic formulas right here. So we have here our power formula, we have here our logarithmic formula, we have here our integration of exponential functions, integration of trigonometric functions, and inverse trigonometric functions. So another basic formula that is not included in this table right here is what we would be calling the integration by parts. So your integration by parts can be represented using this formula right here. So if you are to get the integral of a certain function u times dv, this is to be equal to u times v minus the integral of v du. Okay, so once again, the first thing that you would be doing if you are to be given a certain indefinite integral is to check if these equations right here can solve your problem or can integrate the equation that you are trying to integrate. But let's say that you would be given a certain equation wherein you cannot use any of this directly, so any of these formulas right here. It is then where you can try to use integration by substitution. So once again, in emphasis, you can try, but it does not guarantee that you can solve for it using integration by substitution if you are given a very complicated formula. But this is just one way. So this is your next resort. And by the way, guys, your integration by substitution can be categorized in these two, categories right here. So the first one is what we would be calling the integration by algebraic substitution. So this is to be algebraic. And the other one being the integration by trigonometric substitution. So guys, your integration by algebraic substitution is quite more flexible than that of this trigonometric substitution right here. So for you to understand it better, I would be giving you an example later on for you to realize that using algebraic substitution is quite more flexible than that of your trigonometric substitution. Okay, so let's just have an example for us to understand our lesson better. So given this integration problem right here, which is the integral of square root of 1 minus square root of x dx, so let's check if we can solve for it using these basic formulas right here. So this equation right here can actually be rewritten as the integral of 1 minus square root of x raised to 1/2 times dx. So as you can see here, we might want to check if we can use our power formula. So let's check if we can use our power formula. So the value of your n is equal to 1/2, which is this one right here. The value of your u is equal to 1 minus x raised to 1/2, which is this one right here. And the value for your du is to be the derivative of this function right here. So the derivative of that is equal to, 0. So the derivative of 1 is equal to 0. Minus, so let's get the derivative of x raised to 1/2. So this is to be equal to 1/2 times x raised to 1/2 minus 1, which is actually negative 1/2 times this of x. So simplifying this, your du is now equal to negative 1/2 times x raised to negative 1/2 times dx. So it would be this one right here. And as you can see, this equation right here is not to be equal to this dx right here. Thus, we cannot use our power formula. Okay, so since that is to be the case, the next thing that we would be doing is to check whether or not we can solve for this problem right here using integration by substitution. So integration by substitution is actually used to simplify your very complicated equation. And as you can see here, because of the presence of radical, we cannot solve for this one right here using our basic formulas. So what we would be doing here is to introduce a certain variable for this complicated formula right here to be rather simple. So what we are actually doing here is that we are trying to make this equation right here simpler for us to solve for it using any of the basic formulas. So let's say that we would be introducing the variable y. So y is equal to, so let's say y is equal to square root of x. So what I would try to do is to get rid of our radical symbol right here. So guys, disclaimer, we actually have plenty of methods in using integration by substitution, but I would teach you maybe one or two methods of it. So there. So once again, let's assume that your variable y is equal to square root of x. So that is to be this one already. So if that is to be the case, our transformed formula right now is to be equal to, so the integration of 1 minus y raised to 1 half. But take note guys that we cannot integrate this if this is to be d's of x. So from that, let's solve for our d's of x in terms of y. So from that, let's square both sides of this equation right here for us to get the value of x. So that is to be equal to, so y squared is now equal to x. So what I did here was just to square both sides of the equation. And for me to get the value of our dx, I would now be getting the derivative of this equation right here. So I would just be rearranging it. So x is equal to y squared. And getting the derivative of this would give you this one right here. So d of x, or dx, is equal to what would be the derivative of y squared. That is to be 2 times y raised to 2 minus 1, which is, well, 1. So I would just be erasing this part right here. So that is to be 2y times dy. So basically, your dx is equal to 2y dy. And substituting known values, so it would be this one right here to this one right here. So dx is equal to 2y dy. So rewriting it here, this is now to be equal to 2y dy. And as you can see right now, right here, we can now actually solve for the value of this certain function right here using integration by parts. Since you can see we have our u, we have our dv. So once again, our integration by parts can be written as, so integration by parts, the integral of u times dv is equal to uv minus the integral of v du. So once again, reminder guys that this is not to be the only method wherein you can solve for this. This is just one of many. Okay, so there. And for your value of your u, oops, by the way guys, we can actually rewrite this as this. Let's segregate our constants with the variable. So this is to be equal to, so 2 times the integral of y times 1 minus y raised to 1 half times dy. So basically guys, this equation right here is the same as this equation right here. Okay, so let's just integrate this using the integration by parts once again. So for your value of u, so you can choose whether this is to be your u or this one right here, but in my case, I want it to be y. So this is to be my value of u. So from that, differentiating it, so your du is now equal to d of y. So there. Okay, so I would just be moving this to the left. So there. And for the value of your dv, which is, well, this one right here, I would assume that this is to be my value for dv, which is 1 minus y raised to 1 half times dy. So for us to get the value of v, since we need the value of v here, we would be getting the integral of this one right here. So getting the integral of that is to be equal to, so 1 minus y raised to n plus 1, and n plus 1 is equal to 1 half plus 1, which can be rewritten as 1 half plus 2 over 2. So that is to be 3 halves. So there. So 3 halves. So 1 minus y raised to 3 halves divided by n plus 1, which is 3 halves plus c. But it is okay for us not to include plus c yet, since, well, we are dealing with the method by parts and it wouldn't mean that much. Okay, so using these values right here, we can now substitute it with our integration by parts formula, which is uv minus v du. So copying this one right here to be used as a guide, so it would be this one right here, and substituting once again the integral of u dv, so that is to be equal to u times v, and our u is equal to y, and our v is equal to, so this one right here, which is 1 minus y raised to 3 halves divided by 3 halves. So this is to be for your uv. So minus the integral of v du, and our v once again is to be this one right here. So 1 minus y raised to 3 halves divided by 3 halves times du, and our du is equal to dy. So dy. But don't you forget this constant right here. So we actually have this 2 right here. So from that, all of this should be multiplied by 2. So this is to be this value right here. Since this equation right here is only to be this one right here. So don't you forget this value of 2 right here. Okay, so from that, let's solve for this already. So distributing this value of 2, this is to be equal to, so 2 times, so this is to be 2/3, since this is to be 3 halves. So 2/3 times y times 1 minus y raised to 3 halves minus 2 times the integral of, once again, 2/3 times 1 minus y raised to 3 halves times dy. So, okay, simplifying this further, this is to be equal to, so 4/3 times y times 1 minus y raised to 3 halves minus 2, so 2 times 2/3, so this is to be 4/3 once again, so 4/3 times the integral of 1 minus y raised to 3 halves times dy. So getting the integral of this, function right here, that would just give you an answer of, so this one right here, so that is to be 1 minus y raised to 3 halves plus 1, so n plus 1, so 3 halves plus 1, and this would be giving an answer of 5 halves. So basic math, so 5 halves divided by 5 halves, so plus c, but let's just include that later. So rewriting this equation right here right now is to be equal to, so 4/3 times y times 1 minus y raised to 3 halves, which is this one right here, minus, so 4/3 times this one right here. So that is to be 2 over 5 times 1 minus y raised to 5 over 2. And simplifying this further, it would give you an answer of, so once again, 4/3 times y times 1 minus y raised to 3 halves minus, so 4 times 2, that is to be 8, divided by 3 times 5, that is to be 15, times 1 minus y raised to 5 halves. So this is to be your answer for this problem right here. But guys, take note that this answer right here is the answer of this particular equation right here. So this one right here, and not the answer of this function right here. So if you can remember, guys, we actually have introduced this variable right here to make it simpler. But once again, this is not to be the problem. Instead, we are solving for this one right here. So what we would be doing next is to substitute these values right here once again to your answer. So what you would be doing is that you would be substituting this value to your answer of this certain equation right here. So copying these values right here. Okay, so guys, if you can remember, we actually have introduced the variable y to take the place of square root of x for our equation to be much simpler. So right now, what we would be doing is that we would be rediverting it, these values of our y to these values right here. So from that, that is to be equal to, so equal to 4/3 times y, and our y is equal to square root of x times 1 minus y, which is once again square root of x raised to 3/2 minus 8/15 times 1 minus y, which is once again square root of x raised to 5/2. But don't you forget, guys, the value of your c, or your arbitrary constant c, so plus c. So from that, this is now to be your answer for your problem. The answer of this integration problem right here, which is the integral of square root of 1 minus square root of x dx, is equal to 4/3 times square root of x times 1 minus square root of x raised to 3/2 minus 8/15 times 1 minus square root of x raised to 5/2 plus c. So this is to be your answer for this particular problem using the equation that I have solved for earlier. But once again, guys, this is not to be the only way for you to solve for this equation right here using method of substitution. So it would be up to you on where you would be substituting your value for your y. Okay, guys, so once again, like what I have said earlier, that the method that we did here is not the only way for you to solve for this problem right here using method of integration by substitution. So as you can remember, what we did earlier was that we have substituted the value of y for the value of square root of x. But actually, guys, we can substitute our variable y with the whole equation right here if it would give you a much simpler equation. So from that, let's say that y is equal to 1 minus square root of x raised to 1/2. So let's say that that is to be your y. And using this equation right here, let's now solve for the value of this one right here. So from that, squaring both sides, it would give you an answer of y raised to 2 is equal to 1 minus square root of x. So from that, your square root of x is now equal to 1 minus y squared. So that is to be the case here. Okay, and after that, squaring both sides once again, so your value of your x is now equal to 1 minus y squared quantity squared. So we have this value right here already. So for us to get the value of our dx, so dx is equal to, so getting the derivative of this, that is to be 2 times 1 minus y raised to 2, 2 minus 1 times the derivative of this function right here, which is negative 2y dy. So there. So using the power formula for getting your derivative. So once again, this would go down here. Then this is to be raised to n minus 1, then times the derivative of your function right here, which is negative 2y dy. So simplifying this would become, so negative 4 times 1 minus y squared times y dy. So this is now to be your value for your dx. Okay, so as you can see here, this is to be equal to, so the integral of, and since our y is to be the whole quantity, which is this one right here, this is to be y times dx, and our dx is to be this equation right here. So for our dx, that is to be equal to negative 4 times 1 minus y squared times y dy. Okay, so simplifying this equation right here, this can be written as, so the integral of negative 4 times y squared, so I just multiply this 2 right here, times 1 minus y squared times dy. So from that, we can once again simplify it further in this equation right here. So this is to be negative 4 times the integral of, so what I did here was just to segregate this constant right here. So negative 4 times the integral of, multiplying this term right here to this binomial right here, that is to be y squared minus y raised to 4 times dy. So there. So now let's just solve for the integral of this one right here. So by the way, guys, this can be rewritten once again as so negative 4 times the integral of y squared dy minus the integral of y raised to 4 times this of y. So it would be like that. And we can now integrate these two terms right here individually. So from that, this is to be equal to negative 4 times, so what would be the integral of this value right here using power formula? That is to be y raised to 3 divided by 3 minus, so what would be the integral of this one right here? So that is to be y raised to 5 over 5, so plus c. So multiplying this negative 4 right here to all the terms, so this is now to be equal to negative 4 y raised to 3 divided by 3 minus negative 4 times this one right here, which would give you a positive answer. So 4 over 5 times y raised to 5 plus c. So we now have our answer for this particular function right here. But once again, we are not solving for this one right here. Rather, we are solving for the problem here. So once that you have your answer right here already, what you would be doing right now once again is to redivert it into the equation that has these variables right here. So from that, substituting these values right here to this equation right here, this can be written as, so this is equal to negative 4 over 3 times y raised to 3. So our y once again is to be this value right here. So that is to be 1 minus square root of x raised to 1/2 raised to 3, which is 3 halves. So that is to be 1/2 times 3. So 3 halves. Then plus 4 over 5 times y raised to 5. So our y once again is to be this one right here. So that is to be equal to 1 minus square root of x raised to 5 over 2. So that is for this part right here. So plus c. So basically, guys, this is to be your final answer for the particular problem. Okay, but if you notice that this answer right here, our answer in this problem right here is not to be the same as the one that we have solved for earlier. And even though that they are both the integral of this equation right here, if you would be noticing once again, they have different answers from each other. So the reason behind that is, once again, if you are to get the integral of a certain quantity or a certain function, you're actually getting the function that if you would be deriving it, you would be arriving at this particular answer right here. So what that means is that even though this answer right here is different from this answer right here, if you would be getting the derivative of this certain function right here, you would go back to this equation right here. And if you would be getting the derivative of this function right here, you would once again be going back to this function right here. So even though that they are not the same in nature, but if you would be getting the derivative of both functions right there, you would still arrive at this answer right here. So there.